In 1995, a 340-kilogram machine called the Galileo probe fell out of orbit, slamming into the atmosphere of Jupiter at 170,000 kilometers per hour. Within seconds, the extreme friction generated a wall of heat, pushing 14,000 degrees Celsius, vaporizing the hardware. But right before it melted down, it transmitted a final burst of telemetry. That data confirmed that Jupiter is almost entirely made of hydrogen and helium. Those massive swirling bands make up the single largest untapped reservoir of raw fuel in the solar system. Back on Earth, human civilization is accelerating toward a massive energy deficit. Artificial intelligence data centers run continuously, electric vehicle grids are expanding rapidly, and early plans for space habitats demand more power than current fossil fuels and renewables can generate long-term. To solve that deficit, engineers are building experimental nuclear fusion reactors, like this facility, attempting to replicate the exact process that powers the sun. By fusing atoms together under extreme pressure, we can create limitless clean energy. The most potent fuel for this reaction is a rare isotope known as helium-3. We are rapidly approaching the limit of what Earth can provide to power our growth. The high-density fuel required to break past that ceiling exists in abundance, locked inside the most hostile environment in the solar system. Finding helium-3 on Earth is practically impossible. Our planet's atmosphere and magnetic field allow it to constantly escape into the vacuum of space. Because of this scarcity, researchers have proposed sifting through thousands of tons of lunar dirt, where small deposits get trapped by solar winds. The Moon offers trace amounts. Jupiter, by contrast, has a mass 2.5 times greater than all the other planets combined. Its massive, swirling atmosphere is saturated with millions of tons of this incredibly rare isotope. Because Jupiter is a gas giant, it lacks a solid surface to park a drilling rig. To access that isotope, we have to invent a process called atmospheric mining, deploying massive flying machines to skim the upper layers of the planet and scoop the gas out of the sky. Designing a machine to do this goes far beyond basic aerospace engineering. To pull a usable tank of fuel out of Jupiter, we have to subject our hardware to a continuous physical stress test that pushes modern material science beyond its current limits. The first barrier is simple geography. Depending on planetary alignment, a radio signal from screens like these on Earth takes between 35 and 100 minutes to reach Jupiter and bounce back. In an industrial mining operation, an hour-long delay is a death sentence. If an extraction vessel detects an internal fire or a sudden drop in altitude, real-time human intervention is mathematically impossible. The entire fleet must be autonomous, capable of self-diagnosing and solving catastrophic failures in seconds. This diagram illustrates another major bottleneck, Jupiter's planetary magnetic field. As the strongest field in the solar system, it traps incoming charged particles, creating these brightly colored bands of deadly radiation that orbit the planet. That radiation easily destroys unprotected electronics. When NASA launched the Juno probe, engineers had to house the core flight computers inside this hexagonal vault, made of half-inch thick solid titanium, just to prevent the system from frying as it orbited the planet. Before a single ounce of fuel is extracted, the mining fleet requires heavy metal shielding and highly advanced robotic autonomy, setting a massive baseline cost just to survive the initial arrival. This animated chart shows the depth profile of Jupiter. As the marker descends past the uppermost clouds, the atmospheric pressure violently spikes. Plunge far enough down, and the hydrogen gas actually compresses under the massive weight into a dense state of liquid metallic hydrogen. To avoid that crushing depth, a floating refinery would have to confine its operations strictly to the uppermost layers, hovering in the bands where atmospheric pressure is relatively close to what we experience at sea level on Earth. Yet, staying near the top exposes those machines to the most violent weather in the solar system. These orange-brown vortexes are storm systems where supersonic winds tear through the atmosphere at over 600 kilometers per hour, alongside lightning strikes raging continuously for centuries. While the environment tries to rip the ship apart, it faces an extraction paradox. Jupiter holds vast amounts of helium-3, but the isotope is highly diluted within the broader hydrogen mix. A refinery would have to intake and filter millions of cubic meters of turbulent gas every hour just to accumulate a single barrel of product. Surviving this means engineering a gigantic, resilient industrial megastructure that can strip individual atomic isotopes out of the air while being constantly battered by alien hurricanes. Let's assume the refinery successfully filters the gas and stores the helium-3. The cargo now faces the most unforgiving physical barrier of all, Jupiter's immense gravity well. This chart compares escape velocities. The dramatically taller bar on the right shows that Jupiter's surface gravity is 2.4 times stronger than Earth's. To break free from its orbit, a heavily loaded cargo ship would need to accelerate to 59.5 kilometers per second. The physics of the rocket equation apply a harsh tax here. Generating the thrust needed to push that weight out of deep gravity requires burning a massive amount of highly potent fuel, which often erases the value of the exact resources you just spent millions trying to extract. Aerospace theorists have proposed alternative workarounds, such as nuclear-powered scoop ships. These vessels would skip orbit entirely, skimming the upper atmosphere at high speeds to grab a mouthful of gas before using their momentum to slingshot back to a waiting orbital station. However, this requires structural tolerances that current aerospace manufacturing cannot achieve. The physics audit is clear. Getting close is lethal to electronics. Gathering the product requires filtering a chaotic hurricane. And escaping demands such an immense amount of energy that the whole process risks erasing its own purpose. Right now, pouring trillions of dollars into a Jupiter mining operation makes zero economic sense. Back home, next-generation solar panels, advanced batteries, and terrestrial nuclear fusion projects are rapidly improving, dropping the overall cost of energy on Earth. By the time human engineering is robust enough to survive a dive into Jupiter, our terrestrial grids will likely be entirely self-sufficient. We will not need a gas giant to keep the lights on in Earth's cities. Futurists argue that Jupiter's massive fuel reserve isn't meant for Earth at all. Instead, it is destined to supply a sprawling interplanetary economy, powering cargo routes and floating orbital stations deep in the outer solar system. Operating on that scale requires a technological baseline we are only beginning to conceptualize. We will need heavy industry operating out of hollowed-out asteroids, deep space manufacturing plants, and sprawling fleets of artificial intelligence robots capable of repairing themselves without human input. Pulling helium-3 from a gas giant marks the moment humanity transitions from a planetary species to an interplanetary one, having mastered the most hostile energy source in the solar system.